for 2 minutes. After that, students also understand actually. Those who are listening properly know. So they ask me to disable chat because the moment I switch on, then those people come. So I am taking that in the end and I'm able to manage. Na? Don't worry about it. Yes, a very good morning to all of you. Am I audible and visible to everyone over here? Yes? Audible? Visible? Absolutely fine. There is no issue. Okay. So in the last class, how far we have covered? I think I have given you the concept of hybridization. I think the only, I think we have made the table also, one particular table. Like identifying which particular orbitals are involved, right? Okay, fine. So today we'll be starting off with the that particular concept, like how to calculate the hybridization. So without any further delay, we'll start it off. Okay, and I think I've given you for Priyanka, I've given you also for C2H4 also, beta. C2H4, and I think we have already done for CH4 also. Right? Fine. Okay, so without any further delay, let us get started here. And please pay attention. I'll take your doubts in the end. Okay? That is absolutely fine with you, all of you? Okay, fine. But pay attention to whatever is being going on here. Yeah. Now next is calculation of hybridization. So basically there are, yes, Suhas, I know that, okay, one more is done. That is BeCl2 also I've told you. And I asked you people to read from your NCERT. Like they have given for like few more examples are there, like PCl5 is there, SF6 is given, right? So it is as such understandable, right? So you can read it on your own, right? Now, when it comes to calculation of hybridization, first one is steric number method, right? This you might have already studied in, kind of your organic chemistry, right? But still we are again writing it. And what is the steric number? Steric number is basically number of sigma bonds formed by the central atom plus the number of lone pair of electrons present on central atom. Now, depending upon what is the steric number, accordingly we'll be having the hybridization over here. So if at all I'm having steric number, and if I want to write down the hybridization over here, so if at all I say it is 2, I'll be writing this as sp hybridization. If it is 3, it will be sp2. If it is 4, then it is sp3. If it is 5, it is going to be sp3d. And if it is 6, it is going to be sp3d2. And if it is 7, it is going to be sp3d3. And I hope everyone knows that we are just adding the powers which are there with respect to S and P. So here 1 plus 1, here 2 plus 1, here 3 plus 1, right? Like that it goes. And when it comes to steric number method, basically we are drawing the structure, counting the number of bonds and lone pair on the central atom, and then we are giving the hybridization over there, right? First, make sure that you are writing this, then we'll proceed further. Hopefully written, everyone. Okay. Now let us take few examples. Suppose if we go for NH3, right? So in this case, what do we know? That basically the structure of NH3 is like this. What is the steric number here? Steric number is basically 3 plus 1, which gives you 4. So it will be sp3 hybridized. Similarly, if at all I give you suppose water, so you know that around oxygen we know how to draw the structure now, right? We'll be drawing something like this. Steric number here is also 4. 4 means sp3 hybridized. Getting it? Now, if at all I give you something like CO3 minus 2. Remember we have drawn the structure like this. O minus here, O minus here, putting the lone pairs like this so that the octet is getting completed, right? Now the thing is, what is the steric number for this? It is basically 3. So if it is 3, then it is going to be sp2. Similarly, if at all we go for XeF4, we know that around xenon there are basically 8 electrons, and out of that 4 are getting involved in forming the single bond with xenon, this particular fluorine. So 4 bonds using one single electron. Then also how many remaining? Right? Now the thing is, what is the steric number over here? Steric number will be 4 plus 2, 6, and this will be sp3d2. Right? So only from the structure you know how to draw the structures quickly, so you'll be able to write this. Please write this, all of you. I hope this is clear to all of you. Okay. Now the other method is you can go for division method. So in this division method, what we are going to do is, first you find out, and you better note down whatever is the flowchart which I'm going to make now. You will understand, don't worry about it. Okay. I'll make you understand with the help of example. At present, we are just writing down the steps. Okay. So here, calculate the total number of valence electrons present in the species. After that, what you have to check, VE is valence electrons, okay? If the valence electrons are less than or equal to 8, and you have to check if the valence electrons are greater than 8. Okay. So if it is less than or equal to 8, then divide by 2. And here if it is greater than 8, then divide by 8. Okay. So we are simply first knowing that whatever is the species given to you, you are finding out the summation of the valence electrons of all the atoms which are present in that species, right? That species could be anionic, cationic or neutral, right? And if it is the number of valence electrons is less than or equal to 8, what we are doing is we are dividing by 2. And if at all the valence electrons are greater than 8, then we are dividing by 8 only, okay? Then we are going to see, analyze the basically what is the remainder we are getting in this process. Okay. So here, if or else we'll say that check remainder. Right. For remainder, I'm just using now R. Now the thing is, if R is 0 or 1, we need to see that whether the remainder we got is 0 or 1. If it is yes, and it could be no also, right? If it is yes, then simply what you have to do, Q plus R. Q is quotient, R is remainder, add them to get the steric number. You know? This is basically steric number, and then you can easily predict the hybridization. If at all I'm getting 0 or 1 as the remainder, then simply what I'm doing, I'm adding the quotient and that remainder. Remainder could be 0 or 1, right? And then suppose Q plus R I'm getting as 2. So I got that, okay, steric number is 2. So it should be sp hybridization. If Q plus R is 5, then you got steric number is 5 and it will be sp3d. I hope this is clear what I'm saying, right? Now, if it is no, then we need to check. If remainder is less than or equal to 8, or else if remainder is greater than 8. If this is less than or equal to 8, divide by 2. If this is there, divide by 8. Getting it? It is same thing. Earlier we were dividing the valence electrons, now we are dividing this particular remainder, right? Now, what we have to do, till what time you need to carry out this division process? Till the time you get either 0 or 1 as the remainder, right? So carry out the division till you get 0 or 1 as remainder. And then simply after that, what you have to do? Add all quotient plus remainder to get steric number, to predict hybridization. Okay. As such, you first note it down and then we'll proceed. Hopefully earlier part you people have noted down. It is simple method only. Maybe we have just written it in a kind of flow chart. Then maybe you might feel that it is somewhat which method is this, but it's very simple. Don't worry about it. Yes, are we done writing? Okay. So simply I'll just summarize this method and then I'll take us some example. Okay. Now the thing is, what you have to do in this process, you have to basically just count the total number of valence electron. But first, that is the first thing which you have to do. After that, you have to see whether the total summation of that particular valence electron, is it less than or equal to 8, right? If it is less than or equal to 8, please divide it by 2. Then analyze the remainder of the same division. Are we getting 0 or 1? If we are getting 0 or 1, please don't divide further. Okay. If the remainder is greater than 1, right? This no means what? That the remainder is greater than 1. But how much greater? If the remainder is less than or equal to 8, it is not crossing that 8. Then again divide it by 2 until you get 0 or 1 as the remainder. Right? And then simply you have to add all the quotient and remainder to get the steric number. Right? This part fine, clear, understood what is happening? I just explained one part of it. Okay. Then afterwards, if at all suppose the summation of number of electrons, total number of valence electrons is greater than 8. So what you have to do? Divide it by 8 only, right? And maybe in that division, if you are getting remainder as 0 or 1, you stop there. And you stop and add quotient and remainder to get the steric number. Okay. Now, it could be a possibility that you didn't get the remainder as 0 or 1. You might get greater than 1. Then again you apply this condition. Is that remainder less than or equal to 8? If yes, please divide it by 2. If it is greater than 8, please divide it by 8. Getting it? Now, let us see few simple examples you will only understand. Suppose I am going for H2O, right? Now, let us say what is the total valence electrons here? 1 in hydrogen, there are 2 hydrogen, plus you are having 6. It is 8. Now the total number of valence electrons is basically less than or equal to 8. So what I'm going to do, I'm going to divide it by 2. And there is a reason why I'm writing like this, because this is telling you quotient, this is telling you remainder, this is going to give you 4, which is telling you sp3 hybridization. Right? I'm not purposely writing like this. I'm not writing like this. I'm writing purposely like this because if the remainder is somewhat greater than 1, I can do further division here itself. Right? Now, second one, let us say I'm giving you CO3 minus 2. Right? What is the total number of valence electrons here? Carbon 4, 6 into 3, 18 plus 2. Are you having 24? Now, did you analyze the number of valence electrons is 24, which is greater than 8. So, what I'm going to do, I have to divide it by 8 only. So you're writing 8, here 3. So did you get this as quotient, this as remainder? Please add them. You will be getting 3, which implies sp2. Right? Similarly, if suppose I am giving you for, let us say, I3 minus. For I3 minus, what is the total number of valence electrons here? 7 into 3, and you are having total 22. Again, it is greater than 8. So what I'm going to do? I'm going to divide it by 8, and this time I'm going to have a remainder. Are you able to see this remainder is greater than 1? So what I'm supposed to do next? This remainder you analyze, it is less than or equal to 8. So by which number you are going to divide? By 2, right? Then are you going to give this one as the answer? Normally, if at all I would have written like this, then 3 would have been quotient, na? So this is quotient, this is quotient, you are getting the remainder. When you add all of them, are you getting 2 plus 3 equal to 5? So it is going to be sp3d. Did we understand what we are doing in this method? Please write this down. And this you can apply on any species, okay? You'll get it soon. Write this in, then 2 to 3 I'll give you, and anyhow you are already having with you the entire list of Lewis dot structure you might have drawn enough. So for them you can easily calculate. Once we are done writing, please let me know, okay? Fourth one I am giving you, please do it. I3 plus, NO3 minus, NO2 plus. And please do not apply any of this, like this particular method on non-electron species, okay? You have to rely on their structure only. I'm giving you some time, please finish it. Then I'll discuss so that you get some kind of practice of this particular method. It's easy only. So practice makes any human perfect. And once you are done, let me know, okay? Yes, done? Okay. In this, how many total valence electrons? 21 minus 1, 20. Now the thing is, you might have done like this. 8 to 16, did you get 4? Then again, by which number you are dividing? Right? So basically you got 2 plus 2. So you got this as 4, which is sp3. Did we get sp3 hybridization, all of you? Good. Then in this case, valence electrons 5 plus 1 plus 18. Are you getting 24? 24 means you are having 8, 3, 24. You are getting this as 0. So summation of these two, 3 is sp2. Got this? Good. Now, in case of NO2 plus, this is 5 minus 1 plus 12. Are you having this as 16? So for 16, so are you getting the summation of these two as 2, which is sp hybridization? Did we get that? Very good. Now, for N3 minus, again, valence electrons is 15 for nitrogen and 1 for that charge. So again, what we are going to get is 8 to 16. So you got this as sp hybridization. Did we get that, everyone? Okay, good. For BF3, valence electrons is 5. In fact, not 5, sorry, my mistake. It is 3 plus you are having 21. It is 24. So basically again, 8, 3, 24. So the summation of these two is giving you 3. That means it is sp2. All of you got this correct? So this is a quicker method. Only thing is, you just need to segregate the flow chart in your brain and it will be fine. And in fact, it is not even hard. First thing is, you have to just check the valence electrons, whether it is less than or equal to 8 or greater than 8. The same thing we are also, and if at all it is less than or equal to 8, divided by 2, greater than 8, divided by 8. Now, whatever is the remainder, is it greater than 1? Just check that, right? And if that remainder, if it is less than or equal to 8, the same number by which you have divided the valence electrons, here you have to divide it. So, divided by 2, right? Greater than 8 divided by 8. That's what you have to do. Right? Digested? Fine with this, all of you? Can we proceed further? Yeah? Okay, good. Now, let us move ahead for bond angle. So, in short, we are going to write as BA, or else it will be like represented by theta. Now, when I say bond angle, so bond angle is basically the angle between any two adjacent bonds. Adjacent bonds we have to take, right? So bond angle is angle between two adjacent bonds, right? The other thing is, let us go for checking the factors affecting the bond angles. So factors affecting bond angle, and you have to follow in the sequence, follow the sequence. That means after checking this, you have to go for checking this. That is what I mean by following the sequence. Okay. First one is, you have to check for hybridization. Now the thing is, here if at all I am having sp, sp2, sp3. Right? If at all somewhere the hybridization of the central atom is sp, sp2 and sp3, what is the bond angle associated? We know ideal bond angle is 180 degree for sp. Here it is 120 degree and here it is 109.5 degree, right? So accordingly, according to hybridization, we have to check first. And the first thing is to find out the hybridization. Now, another one is, if at all we have to go for hybridization, we have checked, then number of lone pair of electrons present on central atom. Right? And here what should be same? Hybridization should be same. You have checked that first, okay? So here, hybridization same. I have written this in short, okay? Hybridization. So suppose in this, what we are having is CH4, NH3, H2O. Now we know that hybridization here is, for everyone it is sp3, sp3. Here also it is sp3. Now the bond angle which is seen here is, or in fact, let us first see number of lone pair of electrons on central atom. So it is 0, it is 1 and it is 2. And the bond angle which is seen is, this is 109.5 degree, this is 107.3 degree, this is 104.5 degree. Now what is the conclusion which you are able to draw from here is, you don't have to remember the bond angles, okay? Now the thing is, what is the pattern or conclusion which you can draw from here is, as the number of lone pair of electrons increase on central atom, what is happening to the bond angle? It is decreasing. So are you able to see, in case of ammonia, you had one lone pair, and in case of water, you had two lone pair. So there will be like lone pair repulsion. Because of that, there will be like more of lone pair, bond pair repulsion, and hence, who has to bear the brunt of this repulsion? This bond angle is going to get reduced. Are we clear about it? Please write this. Hopefully, first point also you people have written. Please write this, then we'll proceed further. Yes, are we done writing? Okay. Now, let us proceed further. After that, we need to see size or electronegativity of central atom, right? So, in this case, let us say I am writing here NH3, PH3, you are having ASH3, you are having SBH3, right? Now, the thing is, hybridization over here is, it is sp3, and here they do not undergo any hybridization, okay? No hybridization. And the number of lone pair of electrons, here it is 1, 1, 1, 1, right? Now the thing is, the bond angle which is seen here, right? It is 107.3 degree, then you are having 93 degree, 92 degree and 91 degree. So are you able to see when they are not undergoing hybridization, their bond angle is closer to 90 degree, right? Now, what conclusion you can draw from here? Can I say bond angle is inversely proportional to the size of central atom? As we are moving down, because the surrounding atom is same, nitrogen, phosphorus, arsenic, antimony, what is happening to the size of it? Size is increasing and you are able to see the bond angle decreasing. And what about electronegativity? It is directly proportional to electronegativity of central atom, right? Because down the group when you go, electronegativity decreases, electropositivity should increase in general. So what is happening here? Electronegativity of nitrogen is more, its bond angle is more. Of phosphorus it is less, so bond angle is less. You don't have to remember this. Getting it? Please write this down. Yes, are we done writing it? Then the fourth one is size or electronegativity of surrounding atom. So in this case, let us say I am having PF3, PCl3, PBr3 and Pi3. Now here all of them, they are basically sp3 hybridized, here also all of them. And when we talk about the number of lone pair of electrons, you are having just one electron over here. And then central atom, if you look for, they all are phosphorus, right? Now the thing is, bond angle which is observed here is 98 degree, 10, this is 100 degree, then 101 degree and 102 degree approximately, right? So what conclusion you can draw? You don't have to remember this. What is the conclusion which you can draw basically from here? Bond angle is is it directly proportional to the size of surrounding atom? And is it inversely proportional to electronegativity of the surrounding atom? SA is basically surrounding atom. Are you able to see that? PF3 and PCl3. You can also understand like this. Suppose you are having PF3. This is the lone pair. You are having PCl3 also. Now, which is more electronegative out of fluorine and chlorine? It has to be fluorine, right? Most electronegative element. So, is it going to draw more electron density from this bond? So, you'll be having a delta plus here, and here it will be delta plus dash. Now, out of this delta plus and delta plus dash, which is greater? 1, if at all this is greater. 2, if at all this is greater. Just do thumbs up to understand. Let me know so that first one is correct. First one, right? Okay. Because we know that it is going to create more delta plus at this particular place because this fluorine is more electronegative. So what we do? So more delta plus, and this is lone pair of electrons. So lone pair of electrons are negatively charged, no? So they will be more attracted towards this particular phosphorus. That means this particular phosphorus in PF3 is going to hold on to its lone pair of electrons nearer to it. So what is going to happen? If this lone pair of electrons is nearer, more destruction caused by it, more lone pair bond pair repulsion, and the angle reduction is there. And here it will be slightly little bit away from it. So because of that, relatively less lone pair bond pair repulsion, and that's what is even visible in the bond angles. Understood? So basically, bond angle is directly proportional to the size of surrounding atom. You can think of steric crowding is there because of that more repulsion, and hence the bond angle is going to increase. Right? So you remember either of the thing. That means either you remember with respect to size for central atom and surrounding atom, because the thing is, if at all you remember with respect to size of surrounding atom, you can easily visualize that, okay, if it becomes bigger in size, then more steric crowding, more repulsion there, and the bond angle is going to increase. Right? So for central atom, it is inversely proportional to the size of it. And size and electronegativity of a particular surrounding atom or else central atom, they are inversely related. Please write this down. Yes, are we done writing? Okay. Now there is one small thing which we are going to write here, bond angle around oxygen. See, on oxygen you will be having two lone pair of electrons, and imagine that there are like two bulky groups. On the either side of it, bulky groups are attached. So in that scenario, theta becomes greater than 109.5 degree. So what are those bulky group which could be there? So basically you can have Cl bromine iodine. Here also you can have Cl bromine iodine. Here also what you can have is like CH3, ethyl, methyl, like that. Here also CH3. And you can also have tertiary butyl here. Right? So what happens? Normally we think that, okay, lone pair repulsion will be more because there are two lone pairs here. So accordingly the bond angle should reduce. But here what has happened because of these bulky groups? So there is like more steric repulsion here. That's because of the crowding here. What has happened is the bond angle has increased more than 109.5. And this particular thing will be more useful when you kind of learning organic chemistry there, right? Yes, are we done writing this? Okay. Now, I'm going to give you some question. Please compare the bond angles here, then I'll discuss. Compare the bond angles in following. Please compare. Please do them. I'm giving you some 5 minutes of time. Please utilize it, and I think hopefully you'll be able to do that. In sixth one, accept this NO2 because that is odd electron species. So for that you can leave. For rest of them at least you can arrange. Right? Yes, are we done doing it? See, in first case, what we might have got, did we do like this? Which is actually wrong. Bond angles will be equal. What you are having is, around boron, you are having all the fluorine atoms, all the surrounding atoms are same, and you are not seeing any lone pair there on the central atom. So basically it is a regular geometry. So if it is a regular geometry, so whether you change fluorine by chlorine, all chlorines or all bromines, ultimately it is going to be a trigonal plane and a perfect. So that has to be 120 degree. Now the similar thing happens with this third also. All of them, they are regular tetrahedron, right? So what do we mean to say by this is that if at all a species has got a regular geometry, when I say regular geometry, that means the surrounding atoms are same and you are having no lone pair of electrons on the central atom. In that case, there is no effect on the bond angle whether you are changing the electronegativity of the surrounding atom or the central atom. Getting it? Now, BF2, did you get this as sp hybridization, this as sp2, this as sp3, this as sp3d2? Now in this case, definitely we are going like this only, and in case of sp3d2, please consider the smaller that 90 degree angle, right? Now in case of OF2, OCl2, OBr2, OI2, Fluorine, chlorine, bromine, iodine, they belong to the same group. So always in a group, size factor dominates. So according to the size of surrounding atom, you decide. In case of fifth one, you are having nitrogen, phosphorus, arsenic. Hai na? So when the size of central atom increases, bond angle decreases. Now, in case of OF2 and H2O, here for fluorine, hydrogen, hai na, decide by electronegativity only. Don't go by size. Okay. So the thing is here bond angle will be greater for in case of whom? In case of water, right? So you have to take care that if at all fluorine, hydrogen is there as a surrounding atom and you are comparing same central atom, then you are comparing by electronegativity only, not by size. So basically this is going to be delta plus, this is going to be delta plus. Here what is going to happen? Oxygen is more electronegative, na? So it is going to attract. So this is going to repel the lone pair of electrons. So lone pair of electrons are slightly away. So less repulsion. Here, delta plus on this oxygen because of this fluorine, it is going to take that lone pair near to it. And because of that, more lone pair repulsion, and hence there will be effect on the bond angle. Did we understand? Now, coming to the case of the sixth one. So I'm just utilizing a different space here. For sixth one, you are having NO2, you are having NO2 plus, you are having NO2 minus, and you are having NO3 minus. And I think we have already calculated the hybridization of all of them. This was SP, this was SP2, this was SP2. So definitely this stands out. Okay, fine. This is SP hybridized. Now when it comes to NO2 minus, you might have drawn the structure like this, right? Now, when it comes to basically this structure, NO2 minus I am saying. In case of NO3 minus, are you having this structure? Now in this case, both of them, they are sp2 hybridized. The central atom, they are sp2 hybridized. But here what you have to consider? Lone pair, bond pair repulsion, and here it is bond pair repulsions, right? Because ultimately it is a double bond, but ultimately a bond pair only, na? So lone pair, bond pair repulsions are more. So hence the bond angle is going to be less in this case. So in comparison to NO3 minus and NO2 minus, NO2 minus is going to be less. And here for NO2 plus is going to be at present maximum, right? Now we need to see where this NO2 is going to lie. Now in case of NO2, basically it is odd electron species, right? Now around nitrogen, there are how many electrons? 5. So what we do? We write like this, double bonded O, double bonded O. But when I have drawn this structure, I have violated the octet of nitrogen because what I have done, there are 4 bonds and 1 electron. So basically 9. So 2. We can still better, like make the structure better or correct by just shifting one of the pi electrons like this 1, 2, 3, 4, 5, 6 minus 1, and here it is plus 1. So I can also replace this by a coordinate covalent bond. And this plus minus I can also replace by a coordinate covalent bond, right? Now the thing is, you try to understand this, that there is only 1 electron here, right? And I'm calling this as sp2 hybridization. See, it is odd electron species. Normally, hybridization of odd electron species is not in your syllabus, but since I have given you this NO2, so you just understand if the unpaired electron or the free radical is present on an atom which is connected to more electronegative atom like oxygen or fluorine. In that case, you count its contribution as 1 towards the steric number. That means what I'm trying to say, how many sigma bonds I'm having here? 2 sigma bonds, and there is 1 radical. So 2 plus 1 you count. So you got the steric number as 3. Getting it? That's the reason it is sp2. And experimentally, the bond angle has been found to be 134 degree because 1 electron repulsion, which it is repelling to basically this particular, bond pair, it is definitely lesser than a lone pair or a double bond. So that is the reason we are going to keep it here, right? This is the final order. Getting it? So for odd electron species, you remember that this particular thing you are having sp2 hybridized, and here it is going to be 134 degree, right? Experimentally it is, and here it is basically, it is sp2 with 120 degree, here it is sp2 with 134 degree. Now if at all I give you something like this, a free radical. Now you might have studied that this is sp2 hybridized. Why? Because the free radical, it is present on carbon which is connected not to any electronegative atom. So that's why we are not counting it. We are just counting 3 sigma bonds towards the hybridization. But if the same thing, if I replace hydrogen by fluorine and a free radical here, now I'll be saying it is sp3. Because 3 sigma bond and 1 free radical. So total steric number I am counting it as 4 and hence sp3. Got it? You do not worry about this coordinate covalent bond. At present, you just remember that this plus minus, hai na? Or else you can, if at all you just want a little bit idea, later on I'll teach you, don't worry about it. If this is the case, coordinate covalent bond, normally covalent bond is both the atoms, they'll be bringing one electron. In coordinate covalent bond, only one atom brings both the electron, right? So basically, are we able to see both the electrons are being donated by one particular atom here. So this can also be, this is donor atom, this is acceptor atom. So in this case, this could also be written as A plus B minus. So that's what I've done. This A plus B minus has been replaced by this arrow. Just to give you a little bit idea. Clear? Can we proceed further? Now next is, you can write down a note basically after all this. That particular BF3BCl3 case, we are writing down the note here. If the species has regular geometry, that is, all surrounding atoms are same and there are no lone pair of electrons on central atom, then there is no effect on bond angle on changing electronegativity of either surrounding atom or central atom, right? So please write this. So after this, we are going to learn resonance, so basically, what is this resonance? Let us try to understand with respect to ozone here, right? Now, I'm also going to tell you one generic way of drawing the Lewis dot structure. As such, I have given you the method to draw it quickly. But there could be some issue when it comes to, drawing the Lewis dot structure for those species where resonance phenomena takes place. Like more than one possibility is there, or else pi bonds are there throughout that particular given framework. So there could be problem. For simple molecules, definitely you can draw. Simple molecules only is generally asked for you, right? And as such, it's simple only. What we have to do is count the total number of valence electrons here, 18. Now what do? You connect these oxygen atom. Central atom is also oxygen and the surrounding atom is also oxygen. How many bonds you have made? You have made 2 bonds and the bonds will be made using the valence electrons only. So when you have made 2 bonds, remove 4 electrons from here. So you'll be getting 14. Understood why I have reduced 4 from here? Understood why I have made, or else why I have reduced 4 electrons from here? Because I have made 2 bonds. 2 bonds means 4 electrons, right? Now, the thing is, when it is 14 now left, so these electrons have to be used or distributed in the molecule around the surrounding atom in such a way that their octet gets completed. So here, how many are there around this oxygen? Only 2 electrons. So if at all I put 6 more here, 6 more here, so 12 gone. How many remaining? 2. So you have the option to put it here. Right? So all the 14 electrons, that means all the valence electrons are used up. Now next what you have to do? You find the formal charge. For the formal charge, how many electrons around this oxygen? 7. Right? So it should have been 6 in its valence shell. Similarly here also. How many around this oxygen? 4. 4 means there is a deficiency of 2. But this structure having too many formal charges, it's not good. That means higher magnitude of formal charge is not good. So what we are going to do? We are going to improve this structure. Right? So how we are going to improve? Normally to reduce the formal charge, what we can do is, we can convert 1 or 2 lone pairs into pi bond, right? So I'll convert like this. You'll be getting a structure like this. Are you able to see here? Right? Now if you check the formal charge, I'll just write down the structure separately so that I can directly write the formal charge over there. So here, what is the formal charge? 0, because it is how many electrons around oxygen for the formal charge calculation. You break it only for calculating the formal charge. Here, how much? +1, here it will be -1. So did I get the structure? This one is +1, this one is -1. So this structure is fine. And don't think that, okay, ma'am, one more electron we can convert and we can have, all the formal charge gone. But the problem is, then you have made this molecule gone, because the thing is, you have violated the octet of this oxygen. How many electrons around this oxygen? Total electrons. I'm not asking for formal charge. I'm asking the total electrons. Basically, 4 bond means 8 electrons and 2 electrons here. So that means it will be 10. Getting it? So I cannot have this structure. So only structure here is this one. But if you carefully observe, I have converted this one of the lone pair into the pi bond. I could have done like this also, no? From this side of the oxygen. So can I also expect one structure like this? Right? So this is the second structure. It is possible, no? Did you understand why I'm saying both the structure 1 and 2 is possible? Now the thing is, here, basically, if at all I want to draw the hybrid of this, it will be like sigma framework, we are not doing anything. Partial double bond character we are getting, and delta minus, delta minus. I'm calling this as resonance hybrid, and we are calling them as resonance or resonating structures, RS we say. Or else we also call them as canonical forms, or else resonance contributing. So basically, if at all only one structure existed for this ozone, so bond length of oxygen should have been like 2 bond lengths. One is 148 picometer for single bond length, and the bond length of oxygen double bond was basically 121 picometer. But in reality, the oxygen bond length which we got, that was only 1, and it was intermediate between these two, right? So basically, if earlier scientists, what they thought that, okay, ozone is like this, if at all only one structure existed, right? And then according to that, I should have 2 types of bond lengths existing. One according to double bond, which will be like shorter, and one according to single bond, which should be longer. But when they found out, when they studied this particular molecule, they've identified that basically in reality, there is only one type of bond length which is existing, and that too, it is intermediate of these two, right? So what it tells, that basically there is like possibility of more than one structure for this particular O3. And that's what is resonance phenomena. So resonance just states that basically there is existence of more than one Lewis dot structure for a given species involving the identical position of the atoms. You are not playing with the sigma framework. What you are doing is, are you able to observe just lone pair moving towards the pi bond, lone pair single bond double bond, conjugation should be there. From here also you can get back to this structure. right? And are you able to see the electrons are being delocalized? They are not localized, they are not present on only one atom, they are being shared between more than one atom, right? So that phenomena is also known as resonance. Okay. Now, the thing is, certain misconception will be there in the minds of students that first and second, do they flip among each other? If they flip, please do thumbs up. Do they flip? Sometimes one, sometimes two. Do they flip? Good. Yes, they do not flip. Reason being, they are our imagination, right? We want to, that is our creation on paper, on this board. They don't have real existence. The real thing which exists is this hybrid molecule. To explain its property, we have taken this, their help. Okay, this could be the possibility. This is the way things would be happening. So if certain thing does not exist, then how can we can think it can flip, right? So this symbol is just telling you, okay, this is one of the structure, this is another structure. Are we clear about it? Okay, so I'll write down the definition now and then you can copy it down. The phenomena in which more than one Lewis dot structure involving the identical position of atoms can be drawn for a given species is known as resonance, right? Or delocalization of pi electrons in any species is called as resonance. Yeah? Lone pair of electrons, or else it could be pi electrons also. So please make a note of it and then we are going to proceed further. And 1 and 2, both of these structures look alike. So I can say 1 and 2 are equivalent resonating structures, RS. And this generic method is little bit longer, but it is applicable for any molecule or any species you take, for drawing it. As such, for normal molecules which you get, you can always stick to your, kind of the shortcut which I've told you. Absolutely fine. Here also you could have stick to that, but the thing is only in case of N3 minus and the other like OCN minus, SCN minus, you might face some difficulty. That is the reason I've told you the generic method. Write this, and bond lengths you don't have to remember, okay? Are we done? Please write this down and then we'll proceed further. Here itself in resonance phenomena itself, they can ask you to find out the bond order. Normally bond order just represents the number of bonds which are present between two atoms. Now here, if at all you want to find out the bond order in case of the resonating structure, so you just have to see total number of, we are finding in RS, okay? Total number of bonds between two atoms in all resonating structure upon total number of RS. So suppose if I take O3, you would have drawn something like this, na? Right, here it is plus. And we have drawn one more structure like this, O minus, double bonded O. Here it is like this. Right. Now the thing is, if at all I have to find out the bond order, oxygen-oxygen bond order, so you fix one of the bonds, hai na? Either you take this or you take this, but it has to be the same bond which you are referring to in both the species. So here if this bond, so you have to consider this bond only. You cannot take this two and this two here, right? So how many total number of bonds between the two oxygen atoms here? 3. And what are the total number of resonating structures? Only 2. So you'll be getting bond order as 1.5, right? Now there is one more formula where you can find out the bond order using only one structure, and that is 1 plus number of pi bonds upon the number of sigma bonds. And this please use in the RS only, not anywhere else, okay? For that I am already telling you the disclaimer. Only from 1 RS. So in this case what we are having is, in case of O3, check it from 1 RS itself. How many pi bonds here? Only 1. And how many sigma bonds? 2. So did you get 1.5 bond order? Simple. Apply this only for the RS, okay? That means where resonance is possible. Write this, then we'll proceed further. So if at all I give you another molecule like C double bond O, O minus, O minus, can you tell me bond order of the CO bond? One plus 1 upon 3. Are you getting 4 by 3? That's how we calculate the bond order. Did we get this answer? You need not draw all the resonating structure and check it. You can just see it from one resonating structure. Then suppose if I give you P double bond O, O minus, O minus and O minus. So what you are going to get from here? Bond order of this PO bond. This is going to be 1 plus 1 upon 4. It is 5 upon 4. Getting it? Okay. Now, there could be one more question which can be asked from this is partial charge. So basically, if at all you consider ozone, in case of ozone what we are writing is 1, 2, 3, 4, 5, 6 minus 1, here plus 1. One more structure I am writing na here, O minus 1, 2, 3, 4, 5, 6 minus 1 double bonded O like this. Now are you able to see this plus is not going anywhere? Only thing what is moving is sometimes this oxygen is having minus 1 and sometimes this oxygen is having minus 1. So can I say here minus 1 charge is basically being shared between two oxygen atoms. So for one oxygen atom, what will be the charge? That is going to be minus 1 by 2, and this only I am calling it as partial charge. Right? So for that, they can ask you, or else we can also have the formula which says partial charge is equal to total charge on surrounding atoms upon total number of surrounding atoms. So in case of ozone, for O3, partial charge on oxygen, how much is that? Total charge is how much? On the surrounding atom. So you don't have to add minus 1 plus 1 and make it as 0. On the surrounding atom, it's only minus 1. How many surrounding atom? 2. So are you getting the same answer? Now, suppose if I give you for CO3 minus 2, calculate that. S double bond O, O minus. Calculate the partial charge here on the surrounding atoms. You can write it and then we can discuss this. Here it will seem like this 2 minus 1, minus 2 charge on these two oxygen are being shared with all the three. Or else from the formula, partial charge over here is going to be minus 2 upon how many surrounding atom? 3. And here, partial charge on oxygen, that is going to be minus 2 upon 4, which is minus 1 by 2. Yes? Now I'll ask you to make the structure for N3 minus, which is azide ion. Please give it a try. Like the way we have drawn for O3, please give it a try for N3 minus. And then I'll discuss it. Don't worry about it. Please give it a try. In case of N3 minus, total valence electrons, here don't apply any of that shortcut which I've told you, because if you remember in that shortcut I've told you only about hydrogen, halogens and O minus as the surrounding atom. N minus wasn't taken, right? So that is the reason you can go by the generic method. 15 plus 1, 16 electrons. Now what you need to do? Arrange them like this. Out of 16, 2 bonds made means 4 electrons gone, 12 remaining. So put those lone pair of electrons like this. What is the formal charge on this? Total 7 electrons around nitrogen. There should have been 5. So extra of 2. Here also extra of 2. There is deficiency of 3. Because there are only 2 electrons around this. Right? So this structure I am discarding. Reason being higher magnitude of formal charge. But still I can make this structure better. So how? I can have 2 lone pair of electrons getting converted into pi bond, and when I'm converting it I know that I'm not violating the octet of nitrogen. That is the reason simultaneously I have taken 2 lone pair of electrons and made the pi bond. Are you able to see that? What I've done? This lone pair of electrons made a pi bond, this lone pair of electrons made a pi bond. Right? Now in this case, if you observe, this is minus 1, plus 1, minus 1. This is the formal charge. Right? Now, if at all I draw another resonating structure, another possibility of it, can I draw like this? A lone pair of electrons going to make pi bond, but I have to move one of the pi bond into lone pair of electrons, because the thing is, if at all I don't move, suppose, if at all I keep it like this. So are you able to see you have violated the octet of this nitrogen? You cannot do. So you are having resonance condition on lone pair, single bond, double bond, conjugation like. So basically what you have to do, if at all you move it like this, So 1, 2, 3, 4, 5, 6, you are having N here, triple bonded N. Are you able to get that? So 0 formal charge, +1, and you are having -2. This is the second structure. Can I get another structure like this? If at all I show you by another arrow, let us say by this. I can also move it like this, and in response to that here. So I could have got N triple bonded to N, and then like this 1, 2, 3, 4, 5, 6. This is -2, +1, and 0. Did I get this 3 structure? These are the possibility, right? So these are the various resonating structures. Okay. Now, if at all I want to compare the stability, as such stability and all those points, you will be learning in detail in GOC. At present, since the structures are there in front of you, for this particular structure only I am going to say. Now you are having 1, 2, 3. Are you not able to see these 2 and 3? They are seeming like equivalent, similar to each other. You are having N triple bond, you are having here also. Middle nitrogen, it is having +1, here also +1. Here nitrogen is having -2, here also the terminal nitrogen is having -2. So they are equivalent. So when the structures are equivalent, their stability is also same. Now you compare between 1 and 2. In 2, are you having higher, 2 and 3, are you having higher magnitude of formal charge? So higher magnitude of formal charge is never good. It is less stable. So the order becomes like this. Clear about it? So as far as inorganic chemistry is concerned, the scope of asking something from resonance is limited, but from organic definitely the extent becomes more. Right? Okay. So any doubts for you people? Let me know. Clear to everyone? Stability of 1 and 2. See, what you are going to compare here is, first of all, 2 and 3, they are same, no? Similar structure I am saying. Now, out of 1 and 2 or else 1 and 3, what I am going to see is here you are only having -1, +1, -1. That means the magnitude of the formal charge is less. Here what you are having, are you having -2 there? Magnitude is more, na? Just the magnitude you check. So higher magnitude is going to be like less stable. So the structure which is having higher magnitude of the formal charge, that is not much stable. So that is the reason we have not included this now. Otherwise, this is also a Lewis dot structure, but not the proper one. Getting it? Understood? Okay. Now somebody asked me about OF2 and H2O. Basically, I asked you that please don't compare this using the size factor. For hydrogen fluorine, always compare the electronegativity factor. So here this fluorine, it is more electronegative now, so it will withdraw the electron density from fluorine. So will it be having delta plus here on oxygen? Here oxygen is more electronegative. So this is going to withdraw the electron density towards it. So the thing is here it is delta minus, which is going to repel the lone pair of electrons little bit. So lone pairs, if they are away from the central atom, so they are going to cause less repulsion, and hence bond angle is going to be more. Here this lone pair of electrons are going to be relatively little bit nearer to this oxygen because delta plus is there. And if they are nearer, then it is dangerous because they are going to cause repulsion, more repulsion, and hence bond angle is reduced. Are we clear about it? You can find out, but Abhiram, but there are certain limitations with the N/2 rule. If at all you are using, you can use, not an issue. But the thing is, for N3 minus, for those structures where resonance phenomena is happening, you are going to get some like problem with that. That is the reason you can stick to that N/2, not an issue, for finding out hybridization for simple molecules. And normally NT asks simple molecules only. But if at all you come across anything like the species where more than one resonating structures are possible, which I just now told you that it is N3 minus, OCN minus, cyanate ion, thiocyanate ion. So at that time you can draw their structure and you can rely on it, or else you can go by the division method there, right? In the rare phenomena. Clear? Okay. Fine. So that's all for today. See you in the next lecture. Okay. Thank you and have a nice day.